All right, good morning, everyone, or good afternoon. Unfortunately, my camera died while we were doing the review session, and so I promised I would put some of this material online. So I'm going to do this using the iPad. I apologize for any background noise. So essentially, during the review session, the bulk of it was spent discussing these two problems from the textbook. Problem 7.3 and the next one, I believe it's 7.11. And so these are from the homework problems that were assigned to you in Chapter 7. So I'll spend some time briefly going over these. Problem 7.3 asks us to use the differential equation approach to find V out for time is greater than 0, obviously for this circuit below, and plot the response. One thing that's important to note here is that the switch is closing at time equals 0 and not opening. So we spent some time during the lecture talking about the basic steps that are used to solve problems like these, and so we're going to be using those basic steps. The first one is to calculate the steady state value for the state variable, which here is the voltage across the capacitor, before the switch toggles. And so this is what the circuit is going to look like before the switch toggles. Essentially, the left-hand side of the circuit, including the 6-volt source, will be cut off from the rest of the circuit. Now, what we have here essentially is a single node pair. If I were to draw the closest comparison to a topology we're used to seeing. And for this single node pair, normally KCL is the most interesting description of what's going on. So here we have used KCL to describe the sum of the three currents together, where I1 is the current being supplied by the source, IC is that flowing through the capacitor, and I out is the output or the current that we're interested in. So what we're going to do is here and here we're going to replace our currents with their equivalent descriptions using Ohm's law, and then here we will replace it using the VI relationship for the capacitor. What we end up with is an equation that looks like this, and we're going to plug in our actual value for our C. We are going to sum together the components that are associated or that are coefficients of VC, and we're going to pull our constant over to the other side. This ultimately is going to be our external force applied, which we will often use the letter capital A to represent. All right, so one last thing that we have to do to make this fit our standard form is to get rid of the coefficient of the first order derivative, because the standard form that we talked about in the beginning of Chapter 7 is dx dt plus some value lowercase a times x of t equals a constant. So if we get it in this form as shown here, our value for lowercase a is 2.5, our value for uppercase a is 5. And so this, all of this right here, this is our equation in the standard form. So what's next? Next, we are going to take our predefined form for the solution, which is shown here. Okay, K1 plus K2 e to the negative t over tau. And we are going to take that defined form and plug it into the differential equation above. When we plug that in, what we end up with is this right here. In this part, we have substituted in the particular solution. In this part, we have substituted in the complementary solution. And once we make our simplifications, what we'll see is that we can divide the equation into two constraints. One is associated with the coefficient of e to the negative t over tau, and that will have to equal 0. The other is the essentially is the constant term. So 2.5 K1 must be equal to 5. So we take that, and that turns into our two algebraic constraints. One, again, is that 2.5k1 must be equal to 5. The second is that the coefficient of e to the negative t over tau must be equal to 0. So we take these two, 1 and 2, we solve them, and we get a value of k1 equals 2. We also get a value of tau equals 1 over 2.5. Now we are still missing one value. We have k1, we have tau, but we're still missing k2. And so the next step that we use is we set the solution itself, k1 plus k2 e to the negative t over tau, equal to the initial condition, which in this case was 0. We also have to plug in a value of t equals 0. And so e to the 0 will equal 1, which will leave us with this solution here. k2 equals negative k1 equals negative 2. And so our final solution is shown here. We have our k1 minus k2 e to the negative t over tau. Or VC of t equals positive 2 minus 2 e to the negative 2.5t. Now, it was not VC that they actually asked us for, but V out. And so in order to calculate V out, we can use a voltage divider, right? Because we're interested in the output here, and we know the input here. So the ratio between those two will be 4 over 2 plus 4. And that is what is shown here. So we multiply that by our previous expression, and we end up with 1.33 minus 1.33 e to the negative 2.5t. Remember, or note, that the voltage divider does not affect the time constant. It only affects the beginning and end values. So this is one really great example of a Chapter 7 first order transient analysis problem that you could see on the exam. All right, now the other problem that we're going to look at is 7.7. And so this is really the same type of problem, but just with a slightly more complex circuit. So again, use the differential equation approach to find IOT for t is greater than 0 in the figure below. In this case, what we have is a switch that opens at t equals 0. So these steps should be pretty fresh in your mind. Step number 1 is to solve for the state variable at t equals 0 minus. Now, this is what the circuit will look like in the steady state. Because the switch is closed, the circuit will be relatively large. Obviously, we have to replace the capacitor with an open circuit. Now, how do we solve this right here? Here is where we get to a point, an important point, which is the exam is cumulative, even though we may not explicitly be testing nodal analysis and mesh analysis, because we're going to need nodal analysis or something similar in order to solve this circuit. And so I think one of the more interesting parts of this problem is how I set up the nodal analysis. So we're going to intentionally set node C, which is right here, okay, as the reference node. So we have node C, we have node B, and then we have node A. Normally, you would expect node A to be set as the reference at the bottom of the circuit. That's just the way it normally works out. So why did I do it this way? By setting node C as the reference, we now have a nodal analysis case where there is a independent voltage source between a reference and non-reference node, between B and reference. Whereas if I used the ground down here, we would have to essentially represent B and C as a supernode, which is more work. So it's very explicit the way that I set up this circuit in order to solve. And again, these are the kinds of things that you should have at least relatively fresh in your mind so you can get through the circuit analysis parts of these problems. Nodal analysis, mesh analysis, or using some combination of equivalencies. All right, so now what is this equation here? Where does it come from? It comes from essentially the by inspection nodal analysis method. We initially had 3 nodes here, which means that we should be using or solving for the voltages using a 2 by 2 admittance matrix. However, we know what VB is, 12 volts, so therefore our 2 by 2 will get boiled down to a 2 by 1. And so in this represents our diagonal term, which is the sum of all admittances that are adjacent to node A. We have these two together form a 12K resistor, 12K, 12K, and 4K. Next, we have the admittances that are located in between the node A and node B. And that is, as you can see, a 12K and a 12K. That's this one and these two. Again, I have combined together to be a 12K ohm resistor. So once we work out the math shown here, we have a constant, because anything multiplied by VB will be a constant. So we'll move that over to the other side. And down here, what you can see is essentially the same equation as above, except with all the numbers plugged in. So we have 2 times 10 to the negative 3 equals 5 times 10 to the negative 4 VA. So our VA value will be 4 volts, our VB value will be 12 volts, and our VC, or the V reference, will be 0. And so this is the answer to our nodal analysis. And as you can see, it takes a little bit of work up front to get that first step down. We can defer, use that value of VA to acquire our value of the voltage across the capacitor. Sorry if there's any confusion of me calling this VC sometimes, but the voltage across the capacitor is going to essentially be VA minus V ref, which, sorry, that's backwards, should be V ref minus VA. And so that'll be 0 minus 4, a positive 4 volts, which gives us a negative 4 as our answer here. Now the rest of the problem is using the same steps that we applied for 7.3. We're going to redraw our circuit for t is greater than 0. This is a single loop, and so normally for single loop circuits, KVL is the most interesting way to describe it. We are going to write our KVL, which is Vx plus V1 equals Vc. Make a substitution for Ohm's law. So both of the voltages will be equal to 3,000 times the current through the loop. We'll then make a substitution where we replace I.O. with negative C dV dt. And the reason why there's a negative here is because looking at the polarity of Vc, it doesn't obey the passive sign convention. And so what we end up with is this equation becomes this down here. Negative 6,000 times C dVc dt minus Vc equals 0. We need to put this into the general form, which means we need to get rid of the coefficient of dVc dt. And we do that, we end up with a value of little a that will be positive 3.33. Now, steps 4, steps 5, same as we looked at for problem 7.3. We take the predefined form of our solution, which now no longer has a K1, and it does not have a K1 because this equation has no particular solution. There's no external force being applied, therefore the particular solution is non-existent. So we take our K2 equals negative T over tau, we plug that into the equation above here, and we work downward as shown by the green arrows. And what we end up with is, again, an equation that tells us tau. Tau is equal to 1 over 3.333. We're going to use our initial condition in order to solve for K2. So K2 e to the negative t over tau, substituting in a 0 here, gives us the value of Vc at t equals 0, which is negative 4, and then K2 equals negative 4. So the solution for Vc is negative 4 e to the negative 3.333 t plus a K1 value which is equal to 0, which we don't care about. The last part here is to solve for I/O of t, which is the actual solution they request from us, not VC. And we'll see here that I/O is this value. So how are we going to come up with I/O? We could try to use Ohm's law, but ultimately that's not going to yield a meaningful expression. The expression that is meaningful is the VI relationship for the capacitor, because we know what VC is. So negative C dVc dt equals I/O of t. Again, the minus stemming from the fact that this doesn't the orientation of the capacitor doesn't follow the passive sign convention. And then the rest of this equation is just plugging in the values, taking the derivative. You know, our negative 3.33 value will be pulled out front as we take the derivative. And what we're left with is this expression here, which is I/O of t equals negative 0.6 e to the negative 3.3333t. This is in milliamps, or times 10 to the negative 3. And so those are two really good Chapter 7 problems that you can use to study for the exam. This was a bulk of what we discussed in the exam review session. There were a couple other smaller questions. Again, I apologize.